In this particular video, we are going to talk about Pythagoras Theorem and its unique proofs. From childhood, we have learned about Pythagoras Theorem. Any people who have passed out middle school, they must have heard about Pythagoras Theorem, and it is one of those fundamental theorems which we never forget. When we were in middle school, we have been learned how to prove Pythagoras theorem using similar triangles, but that was bit of complicated. In this video, we should look at two unique ways to prove the Pythagoras theorem, and these are very genuine and precise. After Pythagoras, many scientists, mathematicians, including physicists, philosophers, has tried to prove the Pythagoras theorem in many different ways, and they has been succeeded in their ways. After 3000 years of Pythagoras, J.A.Garfield come with a unique proof that was very easy to be done. And here is some brief introduction about J.A.Garfield. J.A.Garfield was 20th President of United States of America. Besides of being a politician, he was good in Latin, Greek, mathematics, philosophy, etc. And the next proof is from Albert Einstein, who is one of the greatest physicists of all time, and his proof really impressed me. This is a right angle triangle. Its height has length A and its base has length B, and its hypotenuse has length C. From Pythagoras theorem, we all know that a² plus b² equal to c². We are going to prove this. So what should we do? Just take this right angle triangle, turn it up 90-degree angle and place it here. So in this diagram, this angle is alpha. So this angle has to be 90 degree minus alpha. Similarly, we can define another angles. So this is 90 degree. So in this diagram, let's label all the points. Now the quadrilateral in front of you is a trapezium. So area of this trapezium is equal to area of these three distinct regions. In this quadrilateral, you can see these two angles are 90 degree, so these lengths are parallel. So area of this trapezium will be equal to half into a plus b, because a, b are its parallel sides and the length of height, that is clearly a plus b. So area is equal to half into a plus b times a plus b. And if we calculate it in another way, then you can see that area of this triangle is half into a into b, and area of this triangle is half into a into b, and area of the blue triangle is half of c². So if we equate these two results, then we end up with getting half of a plus b whole square is equal to half ab plus half ab plus half c². A plus b whole square equal to 2ab plus c². Expand the left hand side to get a² plus 2ab plus b² equal to c² plus 2ab. 2ab cancel out from both sides. Now we end up with a² plus b² equal to c². This is what Pythagoras theorem suggests. To prove the Pythagoras theorem in the way Albert Einstein has been suggested, we need to have some concept about scaling the area of a triangle. Suppose this is a right angle triangle and we want to scale it up. In this scaling process, each of the side has been multiplied by same factor. So these two triangles are similar actually. If the hypotenuse of the original triangle has length c, then hypotenuse of the scaled up triangle will have length k into c, where k is the scaling factor here. And if the height of the given triangle is a, then height in the scaled up triangle will be k into a, and similarly we can define the base. In this case, area has been increased by k squared time. Similarly, if we scale the green triangle into blue triangle once again, area will be decreased by a factor of k square. We should use this process to prove Pythagoras theorem. Suppose this is our given right angle triangle whose lengths are a, b, c. Now drop a perpendicular. In this case, we can see two more right angle triangles. Area of the main right angle triangle is equal to area of the green triangle and area of the red triangle and its sum. Let's go back to the main triangle. In the main triangle, if we put this angle as alpha, then another angle will be 90 degree minus alpha. So if we drop the perpendicular, in the green triangle another angle will be alpha, and in the red triangle another angle will be 90 degree minus alpha. From here, our observation is the main triangle and the blue triangle and the red triangle all are similar. We can also notice the main triangle has hypotenuse length c and the blue triangle has hypotenuse length a and the red triangle has hypotenuse length b. Now let's consider a right angle triangle whose hypotenuse length is 1 unit and it's similar to all of these right angle triangle above. So if we scale it up to both the triangles, we can use the scaling factor of area as we have shown previously. So if the tiny triangle has area a, then area of the large triangle will be c square into a, and area of the triangle having hypotenuse length a will be a square into a, and area of the right angle triangle whose hypotenuse is b will be b square into a. Previously we have shown area of the large triangle is equal to sum of the blue triangle and the red triangle. So from here, as capital A is non-zero, so we can say a square plus b square equal to c square. This proves the Pythagoras theorem. This was one of the most unique way I have ever seen.